just as a reminder, I put up this diagram of what the question is asking about. It's the conductivity plotted versus the frequency. So the experimental line is showing red. The green is the band theory. Oh well, I guess the green and the gray are two different calculations from band theory. And the kinetic energy is proportional to the area under these curves. So this question is, I guess, what sets the scale for this area? And if we look in the supplement of the paper with Kazuobashi and others published in Nature Physics in 2009, this is the expression that they use for the kinetic energy. It's calculated from the tight-bonding model, and it's proportional to C naught, the distance between the conducting planes, omega, the plasma frequency squared, and then divided by some constants. So since these other numbers are all fixed, then really the kinetic energy is being set by the square of plasma frequency. And here's the expression for the plasma frequency. It's basically taking the conduction electrons at the Fermi surface, which is enforced by this delta function, and it's summing over all the band velocities. So it looks like ultimately the size of the kinetic energy transferred is being set by the velocity of these conduction electrons. I guess. Next question.
Wait. Is Dimitri here? Anybody wants to comment?
We had a meeting.
Because I have a question about this. It seems strange to me that the transfer to the interband is determined by the Fermi velocity. Right? I mean, that's... I mean, there are people here who know a lot more.
Interband contribution for one band mode.
I can make a comment on that. I think that in BCS theory, I don't remember if there is a square or not, but I think that the amount of energy transferred from the condensate, the amount of energy transferred, which does not go to the condensate, it's about delta over EF, the value of the gap divided by the Fermi angle. It's that, either that or that square. So this is the amount.
If it's energy, it's delta squared over EF.
No, the fraction of the energy.
The fraction, then it's...
Yeah, so it's either delta squared over EF squared or delta over EF. I don't remember which one is that. So I think that's why you can see in these systems that have a very large gap the transfer of kinetic energy. Because you have a gap which is 120 eV, you have EF that's about 1 eV, so you have 1% transfer.
But excuse me, nominally that's all taking place in the Drude part, right? We're asking about, somehow the question is asking about higher energy transfers.
In BCS theory you lose spectral weight, most of the spectral weight to the condensate, and a little bit to the interband.
In BCS there is no interband.
There is no interband in the model, right? So it's all in the tail of the Drude, I would say.
Oh, to the tail of the Drude.
Yeah.
But you lose to the... You increase the kinetic energy, right, in BCS.
So you're saying if I had something that was Drude-like, that got eaten up and most of it went into delta function, but there is a little bit that just got pushed to higher energy.
Yeah, and the fraction of that's delta over EF, maybe squared.
In BCS, it's one band model. There's no interband.
No, but that's the first part of the answer. What happens with the single band? Now we can go to the interband.
So I think that's the amount of energy that's transferred from.
Do we think that the question refers to the pseudo gap underdoped cuprates? Is that what the point is here, or is this? I'm not sure I understand the point of the question.
I guess I interpreted the question as just asking what determines this area under the curve of the optical.
Right, but as some various people, including Gers just now, was saying, if you have a BCS system, then nothing should change in there, right? That should be, well, it's not even in the model. So probably your answer is correct with your interpretation, but I'm not sure that's what was implied by the question. I don't know who asked the question.
But the point is that well, we're not going to ask who asked the question.
No, we're not.
The whole point.
No, I didn't mean that.
But the thing is that there is a kinetic energy transferred from the condensate, and I think this is what Ricardo was answering.
Okay.
This is roughly a fraction
Let's
of
just
delta
talk
over
about
EF.
that. Let's talk about
Then
that.
there is a next order question, is whether it's transferred to something within the same band or to interband,
Right.
and that I don't know how to answer because it just transferred somewhere to high
You need
energy.
to show something showing that.
Hmm?
You need to show that sometimes you go from the from the low energies to the high energies, or the other way around. And in one case, it means increase of kinetic energy, in the other case, it means a decrease of kinetic energy. So I think that's the sense, right? Sometimes you have
I see. So you're
to
saying
steal some
the reason
steps
it's
away from the interband to build up the condensate. Sometimes it's the other way around.
well,
In
but
one
that,
case, you have increase or decrease of kinetic energy.
okay, but that's a question I don't know how to answer. So what happens when I transfer energy from interband to build up a condensate? How to determine what fraction it is?
Oh, I think that the fraction is delta over EF.
Delta being
Now I'm really
Interband.
confused.
No, the superconducting gap.
Sorry, delta over EF is what we
Yeah.
push out of when we open the gap. That's what you just said. Now we
Yeah.
take the interband and I push something into the condensate.
Oh, okay, yeah, okay.
And then I just
But
don't
when
know
you-
because I don't have a model for
Yeah,
that.
when you push out of
Yeah.
the low frequency, it's delta over EF. In, I don't know.
What else? Here, what else can you say?
Well, there are many questions here. One question is, there's a sum rule, right? We know there's a fundamental sum rule. The question is, where's the upper cutoff? Where you should put the cutoff for that sum rule to obey, right? And in one band model, in a Bruder with BCS, simple one band model, roughly at 8 times to delta, less than 10 times to delta if you put cutoff, the sum rule completely recovers.
In BCS.
In BCS, right. So in conventional superconductor. Now in cuprates, that is not the case, and that's what Vitry was showing in his first lecture. So there is so in order to recover the sum rule, you have to integrate, you have to include, in this case, charge transfer. So you have to include the transitions from oxygen band to copper bands. And then only you can recover the sum. So it's higher than 8 times the gap. And that, in some sense, says that the mode physics is involved in superconductivity. So it's not independent. Superconductivity is driven somehow by mode interaction. So that basically means that if you want to integrate out the high energy degrees of freedom, you need to be careful because you can't do it lower than transition from oxygen to copper band. So this charge transfer gap has to be involved in that circuit. That's what. Now this picture is from pnictide work that is inherently multi-band system. And here I don't know how the interband interaction in terms of setting up the gap equation, superconducting gap equations are now multi-gap equations with interaction between the between the bands. And how this is included in this model, I do not know.
So we can all agree that you've answered the 0th order question correctly, and nobody knows the answer to the 1st order question.
Okay.
Right?
Okay.
Next question then. So this question I wasn't entirely sure how to interpret. It says, when comparing cuprates and pnictides, Professor Vazov seemed to say that both materials showed a clear superconducting gap signature. Are you that could be observed in optics. Is this issue settled? And I guess looking through the literature, I didn't really find an argument about whether you could observe it using, say, Raman spectroscopy. As an example, I just put sort of a screenshot of the many results that popped up when I Googled for it. And I guess he did say in his lecture that no superconductivity has been observed along the z-axis in ignites, and that this is sort of a disturbing anisotropy. But other than that, I guess the issue seems to be settled. Would anyone like to comment? Here?
So I think this is not my question, but I think this is probably a reference to an issue from the cuprates, which the optics people know probably better than I do. But I'm going to make a comment because I come from Florida, which is where the idea came from originally, from Dave Tanner's group, where they wrote a paper saying in a clean superconductor you don't see the gap. And the idea was simply that if you go back to the early days of superconductivity, the samples were quite dirty. And so if you, for example, look at the famous paper by Mattis and Bardeen, where you see a gap very clearly in the calculated optical spectrum, the normal state reference is just a flat line, meaning that 1 over tau is a very, very large scale compared to the gap. But in the cuprates, 1 over tau is much smaller than the gap, which means that you eat out a very tiny fraction of the Drude weight, and it makes the gap much harder to see. So in the early days of the cuprates, there were a lot of misidentifications of some feature you saw in the optics spectrum, which was probably something else besides the actual gap, because the gap edge was sort of hidden because so little of the weight corresponding to that edge was left over in the Drude peak. So I think that theoretically and experimentally in the cuprates this is now pretty much understood, and so it's resolved in the sense, or settled, I guess. In the nictides, I don't know.
No, I think that in nictides you have to use the Rashberg theory and then you get the right gap.
Yeah, but
You
this
get
one
threshold-
issue about the cleanliness is
No, you do see a threshold that there is a low MPC, but the amount of the gap energy is too high. So basically you need to show that in the Mattis-Bardeen you have an absorption edge of 2 delta. If you take into account the Rashberg theory, is at 2 delta plus the boson energy. Probability of this is the hosting process. So if you take the boson energy as something like 10 millivolts, which whatever is neutrons putting out, then you get right gap values for the I think that for the cuprates, most of the whole dope you don't see the gap. You see something that's fixed energy. And the electron dope, you do see something that stays with TC. And I think it goes because one is dirty and the other is not.
One's what?
One is dirty,
Yeah,
the electron dopes
yeah,
are
right, are dirty, right.
The whole dope working. But I think that you
What
get
about the multi-gap nature? The fact that you have multiple gaps in the...
That's not a problem because the conductivity is a parallel response, so you just add Mattis-Bardeen. So you're going to see one absorption edge and then extra absorption edge. If your experiment can see that, then it's another issue. If you have enough accuracy. But yeah, theoretically you should be.
And only you.
I guess the answer is Rama, or I think it's okay. So, okay, you can do it for me.
Okay, so to start with, I want to say that I feel quite uncomfortable talking about basic arts with so many experts in the room. But so we had this question, and as a good theorist, I thought, okay, so what's the big deal? So So if we know the energy of our incoming photons, I need to turn on the light. So remembering the basic photoelectric effect, if I know the incoming energy of my photons, and supposing I can measure the outgoing energy of my electrons, I can relate all these quantities with the work function. So the energy of my electron inside my sample, so electron inside my sample will be equal to the energy that I can measure minus the energy of my photon minus the work function, or actually on the way down.
Okay.
So in the sample is what it can measure. Sorry. Okay. So assuming I know these quantities very well, we can remember that if I have on my sample, I have my electron here, let's call with Ki on initial momentum, it will come out of my sample with a final momentum if I have my clock here. And if I can measure the angles, theta and phi, I can find what is the binding energy of my electron. Because outside the sample, I have just a free electron. So this energy is the energy of the electron that I can measure. It is outside the sample. And this is Kf. So I have this, the modulus of my final momentum I can get from the energy that I can measure. So I have the relation of the energy with my momentum, so I can plot my nice dispersion. Because I can decompose it and cosine theta, sine phi, cosine theta, cosine phi, and sine theta. Okay, this is, if I'm naive enough, that's what I was before thinking about it. But it turns out that in the z direction, it's not that trivial. So I write here what's the Kf parallel. So parallel, I mean in the plane, will be just my 2 sine theta. And I will do what my perpendicular would be 2 cosine theta. But I am taking my electron from my sample to out of the sample. So I need to consider the work function that I already considered here, but also another V naught that is due to the crystal. So in fact, I don't have this. What I have is this relation with a V naught that in fact we don't know. We don't have enough information to quantify it in principle. So this V naught makes my life hard. And so I need to make more measurements to quantify this V naught and be able to find my Kz. So I will need to erase things. uniquely define K parallel, but I cannot uniquely define K perpendicular. So if I can find for a definite energy, I have this dispersion, so I have my Kf. And if I vary the incident energy, I can have another dispersion, let's say this. In such a way that I can construct my Fermi surface, let's say K parallel. So I can uniquely define this, but not uniquely define this quantity. So if I try to plot this Fermi surface, it will not necessarily match my symmetry point, let's say my gamma point. So I'll need to shift it a little bit in such a way to tune it to the right K. And this tuning comes from determining my V0. So this was the picture I constructed in my head for that. I'm not sure this is the most brilliant way to explain this, but this is the point. So you can uniquely define the K parallel to the plane, but not uniquely define K perpendicular if we don't know this extra potential to the lattice. So we need to make, if we can scan all the Fermi surface here, and we know the symmetry we expect, we can tune to centralize it in the symmetry points we have, and then determine what's the V naught to construct it in the right position. Maybe you have, the experts here have a more beautiful way to explain that. Any comments?
It captures the spirit of the idea. I think the easiest way to imagine is if you fix the photon energy and if you scan your angles, you're going to make a spherical cut in a momentum space.
Okay.
Because the further out with the theta angle, right, the bigger parallel component you have and the smaller perpendicular component you have. Okay? Now if you increase the photon energy, you're going to make a cut in the momentum space a slightly larger radius. Right? Because as you increase energy, the momentum has to expand, increase. So for each photon energy, you're making a spherical cut, and from this you can reconstruct the whole crazy dispersion. Now the point is, as you pointed out, you don't know exactly the offset along the KZ direction. So you can map out the whole momentum space, and you can see the periodicity of the band structure. But there is this V0 component, which is the offset on how to align the center of the brilliant zone, each brilliant zone to its proper position.
But it captures the spirit.
I have a question. What's the physical reason for V0?
For V0,
Yeah.
it's exactly the fact that as electron leaves the sample, right, the momentum parallel to the surface is conserved because there's no potential that is changing. But the momentum perpendicular to the surface experiences a potential at the surface, right? And to reflect this, you have to add this V0. So this is the unknown potential, step potential as the electron leaves the surface.
Well, isn't that just my work function? I know that, right? Isn't that just my work function?
It's not as simple as that. The energy is the work function, but the momentum. You see, the momentum in the photon process is conserved only because of the presence of the lattice. So the momentum of the photon is much smaller than the momentum of the photoelectron, right? So it's not exactly the work function of the material.
Maybe I'll ask you a detail later. Not sure.
No, but you cannot say that, right? Because I mean, it would be work function if momentum was the Quasimodo function. You probably say that Quasimodo is not momentum, so therefore you have to offset it somehow.
Right.
Right? Because in Christie they increase the momentum.
But that's precisely what Adam said. That it's because of the lattice,
Yes.
right?
Right.
That's
But then that's only up to 2 pi. It's a reciprocal lattice very high.
Yeah.
So
Yeah.
it's,
times
I guess,
n times 2 pi.
right, n times 2 pi. So I think that means I don't shift it arbitrarily. I shift it by.
But otherwise it is work function, right? Okay, you can consider your function of operator modulation, no?
Well, experimentally, the work function typically is about 4 eV, right? The value of inner potential it varies with the material very greatly, and it's typically of order of 18 or 19 volts. So just experimentally, we know that this inner potential is not a work function. But the reason for it is the momentum in the photoemission process is not conserved. So it is conserved, but not if you just add momentum of the photon, momentum of the photoelectron, they will not be conserved. So the momentum of the photoelectron actually comes from the lattice itself.
It's like a refraction. The electron, when it comes out from the surface, it gets refracted by the surface. So it's like the light that comes out from the water. You have two different dielectric. You have the same boundary condition. So you can represent this thing on parallel to the surface that is conserved, and the electron when it comes out feels a discontinuity of the potential in the perpendicular direction. So that's why, if I understand the condition correct, I imagine like this. I don't know if it's
Maybe I can move on because
you can describe in the sequence. You know, you work or write or you search your showing the efficiency inside the crystal inside, and you impose that you don't have a discontinuity on the surface, but when you go on the surface, it gets refracted.
Sorry, can you speak up a little bit?
Yeah. Okay, so the question I forgot to here, but it's how we can compare the probing depth of ARDES and the STM magnets. And in fact, I found it a very interesting question because these two techniques are complementary techniques. So in STM, we mainly probe, we mainly have information about the real space, and we probe in K-integrated, we have K-integrated information.
Can you speak loud? Can you speak loud?
Shout at
Yeah,
us.
so, there are two very complementary techniques. By STM, we probe the real space, and we have an integrated information in the K, so we integrate in first approximation over 4K. And by ARDES, we measure in the reciprocal space, and we have information in the reciprocal space. And we can resolve also in K. But the question, in fact, was how we can compare the probing depth of these two techniques, and it's not really related to ARDES, but it's mainly related to photoemission itself. So, in photoemission, we have, so in the base, as Aline was saying, the basic effect of photoemission is the photoelectric effect. So, in the photoelectric effect, you have the energy conservation. Mainly, if you don't consider if you consider just an integrated photoemission spectrum along all the K. So what we can have here, what is represented, in fact, is the density of the state inside the material, and we shoot on the sample a photon with the energy h nu, and so we can, as the energy is conserved, we have a picture of the. So we measure the kinetic energy with the electron analyzer, so we have a picture of the density of the state inside the material. So here, for instance, see the electrons that are coming out from the valence band. They arrive with the photon energy. The kinetic energy is bigger, and the more we at lower and lower kinetic energy, we observe the correlate. But it's okay. This is just in an ideal image. No, in fact, in the real case that we have, an electron needs to pass in the crystal. So what we have to say is that so here we represent the crystal and the cut in the z direction. So this and the sketch of the crystal. So the photons normally have a mean free pass much you know, like always, they have a mean-free path that is much bigger with respect to that of the electron. So we will emit electrons also in the very bulk of the crystal. But what determines the mean-free path in ARPES, in fact, is the probability of an electron to reach the surface of the sample and to be photoemitted without having an inelastic scattering. So this is just a cross-section, is represented like a cross-section process. So it's the effective mean-free path. Here it's, okay, it's just a cross-section of an electron that moved inside the crystal, and it's the probability to be scattered by the active of the crystal. So this decreases exponentially with the distance in the sample. So in ARPES, mainly the problem is quite easy because at the end, one ARPES spectrum, okay, we say this is the electron mean-free path, so it depends on the photon energy. The more surface sensitive measurements are around 50 eV, it increases the low energy. At low energy is mainly sample dependent. As I know, this increasing at higher energy is quite universal, but at low energy depends on the structure of the final state, so it can be quite sample dependent. But mainly, when you choose a photon energy, so you choose a lambda here, so you have an exponential decay, so you will mainly measure electrons coming from the surface, and then you will measure less and less electrons with this. And in ARPES, you integrate overall this, you integrate. So when you change the photon energy, here present for lambda 1 and lambda 2, you just integrate in different areas. So you have information more about the bulk, but it's always an integrated information. So in fact, okay, here what I show these electrons that are photoemitted in the bulk and have some inelastic scattering, in fact, they go in a background. So we lose the information about the initial state, they are scattered, they go in a background here, or in a background here, that you see here. For instance, you see all the 4 levels, and the more electron you photoemit, the more higher will be your vector. And this is something that changes continuously. In fact, it's not, we cannot select just the surface or the bulk. In fact, we can tune the photon energy in order to change the mean-free path, and this is what I show here for some core level of silicon. So here we have, these are the 2 big core level of silicon. So we see that there are many, these are, okay, split by spin orbit splitting, so we have a shoulder here. And this, when we measure the electrons that are coming out with a kinetic energy of 50 eV, which means when we do a very surface sensitive measurement. So we see that mainly there are 2 doublets around here because we observe small shoulders here. So, and what we can do, in fact, is to tune the photon energy. So we go to lower and lower photon energy. It means that the electrons, these 2p core levels, we will measure these 2p core levels with the electron that has the less and less kinetic energy. And what we see is that this shoulder is progressively decreased until we reach the most bulk sensitive measurements of kinetic energy of 5 eV. And it's totally suppressed. So by this information, this is a qualitative information, and we can say that okay, this is more a surface component, and this is more belonging to the bulk. Well, we can just say that this is more related to the surface. Okay, in STM, I'm not an expert of STM, but okay, in STM the situation is much more difficult. If we compare, okay, we still have an exponential decay of the tunneling current, that is what we measure in STM, as a function of the distance between the tip and the surface, or let's say, of the layer we want to go. And if we compare the mean-free path, I think they are more or less the same. So we can say that in ARPES, in ARPES and in STM, we always probe around, if you do ARPES around 100 eV, 50 eV, we always probe more or less the same probing depth. But what is really different between ARPES and STM is that while in ARPES we photoemit electrons and we have an information, as I said, integrated over all the, we have information that is integrating in a continuous way, with respect to the peak, the depth in the sample. With STM, Okay, this I took from the answer that was given in fact by Jenny Hoffman to this question in the Wiki session. So, in fact, in STM, so you can here the tip, okay, you can do what you do, you measure a current. So let's say you can have the current decrease exponentially, so you can measure, you have the main contribution is from the first atom, and then you have contribution also from the underlying layer. But in this case, here you don't photoemit electrons, in fact. So you will measure a current that depends on the matrix element. It depends on the path of your current. You can have some interference effect. So it depends on the matrix element effect that should take it properly into account. So so in fact it's much more difficult than to interpret this as simple replica of the density of the state. But the shape of the orbital and the phase of the difference orbital play a role. So you can have some interference effect. So you can go above, for instance, one atom of copper here in this that you expect that the copper oxygen plane is the metallic plate. So you expect to have a current that is coming directly on your samples. But in fact, this current passes through also the other planes. In fact, you can have some interference effect, and what it happens is that you can have some destructive interference when you are just above your copper atom, and then you can see your copper atom where you move your point, the point of your STM just in another position. So I think I was not very clear. So if you have questions, please ask. But what is interesting for me in this is that in fact, okay, we can say that we can probe more or less the same probing depth. But if we measure a metal, the question I was thinking about is, okay, if you measure a metal, so you have this bulk state, so the electrons are delocalized in all the crystals. So the bulk states of the surface should have some information also of the bulk states, about the bulk states. For sure, we have also some contribution of the surface state that will be more important. But that's why I think, okay, that we can also be sensible to the bulk electronic structure, but this can change a lot from one sample to the other. So it really depends specifically on the sample that we are measuring. So, thank you.
Excellent. Jenny.
I think that you're right that at that minimum in America's curve, they probably do probe about the same depth. And I guess the key is that it falls off exponentially with the distance of the tip away from the sample, and people make the simplification that it falls off exponentially within the sample as well. But as you pointed out correctly, there are a lot of details when you think about what's happening beneath the very top layer.
While in Apples, I think you just integrate. It's much easier to understand because you photoemit electrons, and you know that you will photoemit more electrons from the surface, and the more you go down, you always photoemit electrons, but you have more and more electrons that are inelastically scattered. So you have an integrated information policy. While here, the situation, okay, you can say I have my tip here, I have an exponentially decreasing current, so I have for sure some contribution from these atoms, but you have also strong matrix element effect that come from the path of your current. Through, okay, from the path of your current that should pass through some other orbitals. And this can change a lot. So for me, this is a very interesting.
It's a sample-dependent detail, though. It's not sort of a universal function.
And this is sample-dependent.
Yeah.
In Apples, it's much less sample-dependent, I think. Of course.
Did you have to say?
Yeah.
Well, I have a comment, but Jenny could make this comment maybe.
Well, I don't know what comment you're making, because I can't read your mind.
Yeah, that's right. Okay, so but tell me if you think this is right or wrong. I mean, this is something that I've heard in many STM talks from various groups, that certainly looking at those pictures, and by the way, this is a very interesting article. I don't know. I want to go and read it now. But you get the impression that the STM images or spectra that you see should be very detail dependent. But in practice, at least if you look across families of cuprates, you see a lot of the same features of the copper oxygen plane, regardless of what you're tunneling through. And so the argument has always been made, for some reason we don't understand completely, the details are less important than you might think.
There's
Would you agree with
actually
that?
very little STM on cuprates. I mean, there's BISCO and ACCOC, right? So,
Well, there's two kinds of BISCO, and they have different
well, okay, but they're very
layers,
similar.
right?
No, they have the same. They
They're-
both have the business oxides, I'd say.
Well, but, okay,
So
whether
they
you
have
have
the same
one,
type. The only thing
one
that's
copper
missing is
oxygen
the other.
layer or another copper oxygen layer.
Yeah,
also.
but the top three layers are the same.
Okay, that's fair enough, yeah.
So I mean, I think the place where this interference that he's talking about really comes into play is when you're looking at single atom impurities. And maybe when you're looking at things like the measure of the gap, it doesn't matter as much exactly where your electrons are coming from and what path they took. And much of the STM work is on features of the gap. But what I think this does come into play when you're talking about a single impurity.
But typically the transfer between layers is very small because of large anisotropy in this system. So you are in STM, if we speak of the case of cuprates, you only see the first layer. But let's assume that you take a system which is less anisotropic. Will you be able to feel what's happening a few layers below?
I think only in so much as it affects the density of states of the surface. And I think the argument is similar here. It's a question of what gets to the surface. Whatever gets to the surface is what you see. And certainly there's papers on, there's STM work on semiconductors where they look at dopants and they can distinguish dopants in the first layer, the second layer, the third layer, down to the seventh layer.
They distinguish them because the signature of the signal decreases depending of the depth. I am pretty sure I have seen that.
Right. Yeah, and so I think the point is that it's not that you're tunneling directly into the seventh layer beneath. It's that impurity that's in the seventh layer beneath has some effect, which is 7 layers in radius or something, and so you can detect how far underneath the surface it is.
I have the feeling that in ARPES you can do an effective medium calculation about how the electron escapes from the place where you have interaction with the photon. While in STM you are just measuring the first layer.
Well, in BISCO, for example, the first layer doesn't have electrons. The band is like 1.5 eV away. Yeah, okay, so I
just
think...
metallic layer, because you need to escape on the side, no?
But the point is the electrons have to get there. They have to get to the surface. They have to get there through the strontium and the bismuth. And, I mean, this is controversial, whether people think that this tunneling matrix element has a big effect or not. But I think it's plausible.
It's very plausible because in the comparison with the impurities we did in the NMR experiments, we never will find any density of state on the impurity side in the normal state. So the fact that you see by STM is a proof that you are probing the foreign. This is something which has been discussed already.
Okay.
So the path that we are designing are playing the role in that case.
Thank you. Next. Okay. So following on that, we will talk about
so this question is asking if the 2 magnon excitation, the peak is always at 2 times J. I think the answer is no. Professor Bloomberg has already posted the answer saying that this energy is dependent on J voltage cycle, the exchange constant. Here I want to show another example which shows that which gives a 2 magnon excitation now at 2J. So this is a Heisenberg model with only the layer tables change J greater than 0, and here's we have spin top on each side. So this is the Brownsville configuration. It's a pi for magnetism. And say you have one magnon excitation. Say you have this one. If you flip the spin from down to up, then we have to break those 4 bonds. And if you break each bound, you have to pay an actual energy half J, since each side has momentum speed by half. So for breaking 4 bounds, you have to pay 2J energy. And if you have 2 magnetic excitation, say these 2 magnons are independent, then we should pay 4J. But in this Raman process, what happens is that there's a magnet interaction, and so these 2 magnet excitation could happen at these neighboring sites. So in this case, we should break 6 bonds, and we need to pay 3J energy to get this excitation. And also, this excitation is dependent on momentum. So here, this is the speed wave calculation for this process, and this is done without the magnet direction. So here we found this excitation at 4J, and this is dispersed along momentum. And this is after we include the interaction. So here we got some excitation close to 3J. Yeah. So I think generally this question is the answer is it depends on the ground state configuration, and also depends on the exchange constant, also depending on the momentum. Yeah. So any comments for that?
He approves.
Okay, great.
Okay.
We, oops. Oh, okay. The next question is, what happens, okay, so the question was about renormalization of the Fermi velocity in graphene. And in York's talk, the question was, so when the Fermi velocity in graphene gets renormalized logarithmically, it appears that there's a curvature in the band structure, and this indicates that there may be a sort of quote-unquote negative effective mass in graphene. And so the person who posed the question was trying to draw the analogy to Su Cheng's talk about the quantum spin Hall topological insulators, where you have a topological phase transition when the mass goes from, when the mass changes sign. So you asked, is this the case when you have a renormalization of the Fermi velocity in graphene? Well, so the simple answer is no, because the mass that drives the topological phase transition in graphene, in the quantum spin Hall or topological insulators is the direct mass, and what you're renormalizing in graphene is just the Fermi velocity, or quote unquote the Newtonian mass, or which is the effective mass that you get from the band structure curvature. So probably the simplest way to see it is so for a relativistic system, the energy E squared is so what we end up normalizing in graphene is only the Fermi velocity, and so that doesn't change the topological nature of the system at all, and it's only when you change M that you get a change in the topological invariant, and you see. So the definition of the topological invariant is given by, so the topological invariant is given by given by a tensor product of the D vector over the Williams zone, and this only depends on the sign of the direct mass. So that's the simple answer.
Okay. So, did you have a
the two more questions left, so I don't know if you want to go through that. So
Choose one.
choose one. Okay, so we'll skip the question about RG because that's our textbook question. So there was one question about the presence of node versus no node in the NIC types from RPAS data versus say coherence length or bulk measurements. And what let me read the question in detail.
Well, that's a cruel question.
Yeah.
Anyway,
Many
so
answers.
oh yeah, I'll just paraphrase it. So what it says is there a way to resolve this discrepancy, and what's the community's view on it right now? So this so I'll just throw out one answer. One answer that we thought was maybe there could be a small D-wave component in the bulk, and then due to either surface reconstruction or junk on the surface. So as we know, for D-wave, Anderson's theorem doesn't apply. So if you have disorder on the surface, you could kill the D-wave order by scattering. So RPAS, which is a surface probe, will only see the S plus minus component.
Sorry, can I comment on that? The nodes that we're talking about are not D-wave nodes. All of these are A1G, so they're all S nodes. It's just that because if you look at the higher order function that is higher order than just constant in the S-wave representation, it's perfectly allowed to have nodes at the points away from gamma point. And these are the ones we're discussing.
But Anderson theorem still works there, right? Suppose
Well,
you have some momentum dependence.
you can still lift the nodes, and interband scattering is pair break.
For example.
I think Peter is
I think I was basically saying the same thing. Your argument is totally fine applied to the S-wave nodes, as long as your scattering just scatters primarily within a given band. So if you have some very sort of roughness on the surface of a long wavelength type, then you would tend to scatter with a relatively small Q, and then you'll stay within the band, and fine. You'll just average out the anisotropic gaps on each electron pocket.
okay, great.
And yeah, so
Is that,
spirit is correct again.
is that the real reason?
Oh, I have no idea.
He suggested a way to reconcile, and it's a good way, right? I mean, that's.
There are about 5 other possibilities.
Cases sufficiently to find out whether there are nodes. The point is that you.
That's another important effect. Yeah.
Because those nodes are not expected necessarily in the ground plane.
For electron sheets, I think they are.
Your proposal, you could have nodes which are at different KC. So I have not seen a full map of the superconductive gap in all the K spatial.
It's outside on the poster.
All 5 opposing viewpoints, Max?
This one. There's also, I think, some magnetic measurements by Japanese group that shows nodes along the KZ direction. I can't remember the reference right now. There's some indications.
There's another possibility which might be important for some systems, which is that the electronic structure changes near the surface. And so if you have one of these third hole pockets, which is preferentially preferred by the surface states, then that can stabilize an isotropic state. So any surface state would, in that case, any surface probe would have to see an isotropic case, even if the bulk is anisotropic. But STM and ARPAS should agree based on the earlier discussion. They don't always agree. So I don't think there's any consensus on this.
That's a good controversial point to stop.
Yeah.
Okay.
Thanks, guys. Great job.
Huh?
That was light.
It was when you have enough time to prepare, so it's spread.